When 3I/Atlas is moving through the inner solar system during a period of increasing solar activity, what to expect physically, what should observers pay attention to, and why it is important. Review. 3I/Atlas is an interstellar comet. Designation begins with 3I, passing through the inner solar system on a hyperbolic trajectory. Since it did not form in the solar system, its composition, variability, and physical structure may differ from most local comets. Increasing solar activity, increased EUV flux, more frequent CME emissions and high-speed fluxes, more variable interplanetary magnetic field, has a strong effect on cometary formations and tails due to increased photoionization, plasma interactions, and radiation forces. Why does increased solar activity matter for a comet? The rates of photoionization and photodissociation increase with increasing EUV/XUV flux, changing the balance of neutral and ionized particles in the coma and accelerating the formation of an ion tail. Coronal mass ejections, CME, interplanetary shocks, and large intersections of the heliospheric current layer change the local speed of the solar wind, density, and orientation of the magnetic field. They cause sudden plasma phenomena in comet tails, separation events, reconfiguration, and short-term brightness increases. Increased radiation pressure and heating can increase dust formation or cause fragmentation of structurally weak or volatile-rich bodies. Physical effects and observed signs. Ion tail reaction. Separation events. The CME or the boundary of the magnetic sector can lead to reconnection in the ion tail of the comet, leading to a visible rupture or separation of the tail segment, which is moving downstream. This is one of the clearest signs of space weather. Rapid reorientation or broken morphology. Changes in the direction of the IMF, interplanetary magnetic field, change the direction of the ion tail on scales from hours to days. Changes in ionic composition. Increased photoionization changes the balance of ions, for example, more CO+ or H2O+ compared to neutral substances, and can change the ratio of lines in the spectra. Neutral coma and dust. Brightness fluctuations. Increased heating and the activity of sunlight can increase the release of gases, temporary lightning, or, conversely, fragmentation and erosion can lead to short-term emissions of dust, which then disappear. Morphology of the dust tail. A change in radiation pressure and a sudden release of dust create synchronous/syndine patterns that may indicate the time of the release and the size of the particles. Fragmentation. Heating or pulsed effects can lead to splitting. Fragments can form their own comas and move along slightly different trajectories, detectable astrometrically. Non-gravitational accelerations. Increased gas emission leads to noticeable non-gravitational effects on the core. Tracking these effects limits production volumes and active zones. Spectral characteristics. Stronger emission lines of ionized particles, CO+, H2O+, N2+, if present, radicals such as Cn, C2, C3, and atomic lines in the UV/optical range. The relative intensity of radiation may differ for comets of the solar system. Polarization and properties of dust. Polarimetric changes may indicate changes in the composition or granulometric composition of dust as a result of dust emission caused by sunlight, or its aging under the influence of solar radiation. Recommended observation strategy. Operational coordination with solar observatories. Monitoring of coronagraphs and heliospheric tomographs, SOHO/LOSCO, stereo, solar orbiter, Parker solar probe, where possible, to detect emissions and shocks on the trajectory crossing the comet. Compare time and location to predict interaction intervals. Multi-wave monitoring. The order of priorities depends on the available means. Optical broadband imaging to determine the overall morphology and brightness changes. High-frequency visualization when predicting the intersection of a CME or sector. Comet narrowband filters, Cn, C2, C3, continuum, for separating gases from dust. Spectroscopy, optical/near-infrared/ultraviolet, to measure parent and daughter species, ion lines, and isotope ratios where possible, e.g., D/H if the S/N ratio allows. UV, HST or UV spectrographs, to quantify OH, H, and other photodissociation products and measurement of the photoionization rate. Radio/submillimeter, e.g. ALMA, IRAM, single band, for detecting initial volatiles such as CO, CO2, intermediate lines, HCN, and for limiting core activity. Local solar wind monitors use ACE, SCOV, solar orbiter, and PSP data to determine the local plasma context and time of occurrence of disturbances. Frequency and time. Increase the rotation frequency around the predicted solar events and at a time when the comet is at a distance of 1 to 2 Australian dollars from the Sun, where the solar effect is strongest. Fast shooting even one night before/after an event can capture a disconnect or reorganization. After connecting/reappearing, perform thorough monitoring immediately to identify any changes missed during the break. Astrometry and long-term photometry. Frequent astrometry to detect non-gravitational accelerations and isolate dust and gas effects on the visible position. Photometry with a long baseline to track the evolution of activity. Scientific results and why they are important. Plasma physics. CME's documented interaction with an interstellar comet would provide a unique laboratory for magnetic reconnection, ion capture, and mass gain under various volatile compositions. Composition analysis, spectroscopic detection, or absence, of common and unusual volatiles limits the conditions of formation and processing in another planetary system. Differences in component ratios or isotopes can affect the chemical composition of planetesimals and the thermal history. Dust and core structure. The rate of dust formation, grain sizes, and fragmentation patterns reveal the mechanical strength and evolutionary state of the body, the key to understanding how interstellar objects survive ejection and transit. Population context. Composition and physical behavior compared to 1I/Oumuamua and 2I/Borisov will help to create an empirical picture of the diversity of small interstellar bodies. Uncertainties and caveats. Line of sight and projection. The geometry of the tail unit strongly influences the morphology of the tail unit. Visible kinks or kinks can sometimes be projection effects. Polygonal views, spaceship plus Earth, help to eliminate ambiguity. Data gaps. Solar conjunctions or poor coverage may obscure temporal events, so archive searches and cross-correlation with solar data are necessary. Comet variability. Comets may exhibit flares or fragmentation unrelated to solar exposure. Establishing a cause-and-effect relationship requires comparing time with independent measurements of the solar wind. Practical recommendations for observers and communicators. If you have time to work with the telescope, prioritize narrowband gas images and spectroscopy during the expected interaction intervals and maintain at least nighttime images during the perihelion passage. If you are on a space mission to observe the Sun, archive and mark CMEs that may overlap with the ephemeris of the comet. Publish alerts in almost real time so that comet observers can respond. To attract public attention, use the before and after image sequences and explain the physics of tail separation using simple diagrams. These events make excellent visual stories linking solar activity and the science of small bodies. HiRISE planned for October 3, 2025. Then comet lost to solar conjunction until December 2025, covering what HiRISE could have done, why the conjunction prevented observation, what was missed, how to reconstruct what happened during the gap, why activity may peak after the conjunction, and a detailed post-reappearance monitoring plan. What HiRISE could have measured on October 3, 2025. Spatial resolution and targets. High-rise on MRO can achieve 0.25 to 0.3 m/pixel at typical Mars mapping altitudes. At realistic comet distances from Mars that day, tens to hundreds of millions of km, resolution will be far coarser but still much higher than ground seeing, able to constrain coma structure on 10s, 100s of km scales, depending on range. Key targets: detect compact nucleus or bright condensation, resolve multiple fragments separated by tens of km, image localized jets/active areas emerging from the nucleus, map inner coma brightness gradients and dust fans. Science measurements possible. Direct imaging of fragmentation or nascent fragments, measure their positions and relative velocities. Resolve dust jets and measure position angles to infer rotation phase and active regions. High-quality astrometry tied to the image field to constrain non-gravitational accelerations. Time series imaging during a single MRO pass to detect very short-term variability, rotation or short outbursts. Operational constraints high-rise would follow. Short exposure times to avoid smear, use of red and, where available, color channels to distinguish dust continuum from gas-scattered light. Multiple exposures to enable cosmic ray rejection and to stack for faint structure detection. High-rise planned for October 3, 2025, then comet lost to solar conjunction until December 2025, covering what high-rise could have done, why the conjunction prevented observation, what was missed, how to reconstruct what happened during the gap, why activity may peak after the conjunction, and a detailed post-reappearance monitoring plan. What high-rise could have measured on October 3, 2025. Spatial resolution and targets. High-rise on MRO can achieve 0.25 to 0.3 m/pixel at typical Mars mapping altitudes. At realistic comet distances from Mars that day, tens to hundreds of millions of km, resolution will be far coarser but still much higher than ground seeing, able to constrain coma structure on 10s, 100s of km scales, depending on range. Key targets: detect compact nucleus or bright condensation, resolve multiple fragments separated by tens of km, image localized jets/active areas emerging from the nucleus, map inner coma brightness gradients and dust fans. Science measurements possible. Direct imaging of fragmentation or nascent fragments, measure their positions and relative velocities. Resolve dust jets and measure position angles to infer rotation phase and active regions. High-quality astrometry tied to the image field to constrain non-gravitational accelerations. Time series imaging during a single MRO pass to detect very short-term variability, rotation or short outbursts. Operational constraints high-rise would follow. Short exposure times to avoid smear, use of red and, where available, color channels to distinguish dust continuum from gas-scattered light. Multiple exposures to enable cosmic ray rejection and to stack for faint structure detection. Why the conjunction prevented observation, and what conjunction means here. For ground-based and most Earth space assets, a solar conjunction means the comet's solar elongation became too small, close to the Sun on the sky, so it was not safely observable, daylight glare, very low contrast, and instrument safety/pointing limits block imaging. For typical observatories, elongations below 15-30 degree are effectively inaccessible. For MRO/high-rise, two separate limits can block observations. If the comet's apparent position was too close to the Sun from Mars viewpoint, high-rise would be prevented from pointing for spacecraft safety reasons, direct or scattered sunlight into optics, thermal/stray light limits. Even if Mars had a usable Sun-comet separation, MRO operations constraints, e.g., uplink/downlink windows or avoidance of new commanding during mission events, can limit responsive observations. Practical effect in your scenario: the comet's geometry implied no safe, useful line of sight for Earth-based facilities and high-rise execution was either vetoed or impractical, producing a continuous observing gap until December. What was missed during the October-December gap? Time-critical transient events. Disconnection events or ion tail reconfiguration induced by CMEs or sector crossings. These can occur and evolve on hour-to-day timescales and are easy to miss. Short outbursts or fragmentation that occur and disperse within weeks, fragments that form and disperse below detection thresholds may be lost entirely. Baseline evolution. The rise, peak, and immediate post-peak decline of activity level, dust and gas production, a single gap of 2 months during perihelion/proximal passage can hide the activity maximum. Early development of recurrent jets tied to rotation, which allow rotation period determination, missed rotations reduce ability to link repeated morphology features. Orbital/physical constraints. Accurate measurement of non-gravitational accelerations across perihelion requires continuous astrometry. Gaps reduce precision and can bias derived outgassing parameters. Early fragmentation signatures that would explain later dynamical and photometric behavior remain undetermined. How to reconstruct what likely happened during the gap. Use solar observatory data to look for external drivers. Query SOHO/LOSCO, stereo coronagraphs, stereo/HI heliospheric imagers, solar orbiter and Parker solar probe datasets for CMEs, shocks, or dense streams timed to intersect the comet's predicted path. If a CME crossed the comet during the gap, it may explain a later reappearance signature, e.g., fragments or tail disconnection that becomes visible after conjunction. Use in situ solar wind monitors, ACE, SCOV, solar orbiter, PSP, to reconstruct IMF and dynamic pressure histories and identify likely interaction epochs. Re-examine spaceborne wide-field imagers. SOHO/LOSCO C3 sometimes registers comets close to the Sun even when ground telescopes cannot. Stack and difference imagery to search for faint signature of the comet during the gap. Stereo imagers likewise can sometimes capture comets that are in Earth's blind zone. Archival stacking of near-conjunction observations. Check small aperture solar coronagraphs and heliospheric imagers for faint traces. Temporal stacking, along predicted ephemeris, improves sensitivity to faint, extended emission. Model-based inference. Use preconjunction photometry and activity trends to extrapolate expected gas/dust release, then compare to post-conjunction observations to test for anomalous enhancements, outbursts, or drops. Run thermal diffusion models to check whether thermal lag or surface sublimation wave propagation predicts a delayed peak in activity after closest approach. Why activity might peak after reappearance, physical reasons. Thermal lag in cometary material. Heat penetrates slowly into porous, low-conductivity nucleus material. Peak sublimation of deeper volatiles, e.g., CO, CO2, can lag insolation peak by weeks or months, producing a delayed activity maximum. Progressive exposure and delayed fragmentation. Surface erosion or progressive weakening from perihelion heating can trigger fragmentation after the closest approach, producing a sudden large rise in dust brightness that is only visible when geometry allows. Solar wind/space weather forcing during conjunction. A strong CME or a sequence of solar wind disturbances during the gap can strip volatiles or trigger mass loss episodes that produce enhanced dust/gas release once the comet reappears. These interactions may not be visible until the coma expands back into sunlight and becomes detectable. Viewing geometry and phase effects. A peak in observable brightness can occur when phase angle or Earth/Mars distance becomes more favorable even if intrinsic production peaked earlier. Concrete post-reappearance observing plan, first 0 to 3 weeks urgent, then 3 to 12 weeks follow-up. Immediate priorities, first 0 to 72 hours. High cadence imaging, daily or better if possible, with 1 to 4M class telescopes to capture early morphology and any residual short-lived fragments. Use broadband for S/N and narrowband comet filters, CN, C2, dust continuum, to separate gas/dust. High-resolution imaging with HST/HiRISE, if still possible, to look for nucleus fragments and inner coma structure. Request rapid triggering if the object looks active. Spectroscopy, optical/near IR, to measure gas emission lines, CN, C2, C3, NH2, H2O proxies, CO, and search for changes in composition compared to preconjunction spectra. Fragment search, PSF subtraction and image differencing, stack frames shifted to predicted fragment motions to enhance S/N for faint fragments. Orbit non-gravitational forces, fit astrometry including standard non-gravitational parameterization, A1, A2, A3 or more advanced models, before and after conjunction, compare to test for impulsive events. Composition, derive production rates from spectroscopic line fluxes, correct for fluorescence efficiencies, and compare species ratios to preconjunction values and to 1I/2I benchmarks. Solar context correlation, time tag all observed changes and compare against heliospheric/CME timeline to test causation versus coincidence. Contingency and archival searches. If rapid reactivation is not detected, do deep stacked imaging at predicted ephemeris to place strict upper limits on nucleus size or low-level activity. Search SOHO/stereo/solar orbiter archives during the gap for any weak detections or transient features. These can anchor models of activity timing even if ground assets miss them. A short checklist for observers at reappearance. Night 0 to 3, broadband imaging, R/I, narrowband gas filters, CN/C2, spectroscopy, astrometry. Week 1, ALMA/MM slot if volatile suspected, HST/high-res imaging request if fragmentation suspected. Week 1 to 4, daily photometry if actively changing, otherwise every other night, polarimetry twice weekly if resources allow. Ongoing, maintain coordinated log of solar wind/CME events from solar mission feeds. The lost high-rise observation and the conjunction gap matter, what key science questions are enabled by those observations, and how recovered data after reappearance can still address major problems in cometary science and solar/heliospheric physics. High-level significance. Comets are primitive solar system bodies. High-quality observations across perihelion probe volatile inventories, surface and subsurface structure, and processes that drive mass loss and evolution. Missing time-critical data around perihelion reduces our ability to link instantaneous processes, outbursts, fragmentation, jet activation, to longer-term evolution. A high-resolution dataset from a spacecraft camera like HiRISE offers spatial detail and vantage geometry unavailable from most ground facilities. That detail is crucial for resolving small fragments, jets, and inner coma structure that reveal nucleus heterogeneity and mechanical properties. Key science questions enabled by the lost observations. 1. Nucleus properties and heterogeneity. What is the nucleus effective size, shape, and albedo? Are there active patches or pervasive diffuse activity? Do jet sources map to distinct terrains, e.g., cliffs, pits, implying localized volatile reservoirs or structural weakness? 2. Activity drivers and thermal physics. Which volatiles are driving the observed activity near perihelion, H2O versus CO/CO2? How does activity evolve with changing insolation and internal thermal lag? How does porosity, thermal inertia, and layering control delayed activity peaks or post-perihelion fragmentation? 3. Fragmentation mechanics and evolution. Did fragmentation occur? If so, what fragment size distribution, separation velocities, and timing? Are fragments monolithic or rubble? Fragmentation constrains tensile strength and internal stress regimes, critical for models of comet survival and dust production. 4. Dust properties and production. What are the dust size distribution, mass loss rates, and grain velocities? How do these depend on nucleus activity and solar forcing? Dust composition and morphology, via polarimetry/spectroscopy, inform models of primordial aggregation and alteration. 5. Non-gravitational forces and orbital evolution. How much do outgassing forces alter the orbit? Accurate astrometry before/after perihelion is required to constrain non-gravitational parameters, A1/A2/A3, and to model future dynamical evolution. 6. Solar wind and heliospheric interactions. Did a CME or solar wind enhancement during conjunction trigger tail disconnection, enhanced sputtering, or mass loss events? That ties cometary response to heliophysics and plasma interaction models. 7. Comparative and evolutionary context. Is this comet typical of its dynamical class, Oort cloud, LPC, JFC? Data informs population synthesis, mass loss lifetimes, and the delivery of volatiles to the inner solar system. Why HiRISE, and similar spacecraft, are uniquely important. Spatial resolution and inner coma access. HiRISE can resolve inner coma structures and relatively small-scale jets or fragments that ground telescopes may blur out, especially when the comet is near Mars' vantage geometry. Different solar phase/parallax. Observations from Mars' orbit provide a different phase angle and parallax relative to Earth, useful for 3D coma reconstruction when combined with Earth data. Short integration snapshots with high S/N on bright inner coma regions let us detect compact condensations, fragments, and measure their trajectories precisely. Specific measurable quantities and how they constrain theory. Nucleus radius and albedo constrains nucleus mass, gravitational binding energy, and survival thresholds for fragmentation. Active area fraction and jet geometry constrains whether activity is localized, pits/cliffs, or global, sublimating mantle, which ties to volatile layering models and transport models, e.g., sublimation fronts. Production rates Q, H2O, Q, CO, Q, CO2 relative abundance ratios set formation and thermal history constraints, e.g., CO-rich comets imply colder formation regions or preserved supervolatiles. Dust mass loss rate and grain size index, power law slope key inputs to mass loss budgets and meteoroid stream production, grain size affects coma brightness and radiation pressure evolution. Fragment separation velocities and size distribution, constrain fragmentation mechanisms, rotational breakup versus thermal stress versus impact, and help estimate mass lost in discrete events. Non-gravitational parameters, A1, A2, A3 feed into dynamical models predicting future perihelia, potential meteoroid stream evolution, and risk assessments for spacecraft/planetary encounters. Temporal light curve, AF, and morphology changes help separate steady sublimation from impulsive events. Temporal derivatives can be compared to thermal diffusion models to infer subsurface diffusivity and layering. Broader scientific impacts. Solar system formation and volatile delivery. Volatile inventories and dust composition inform theories of volatile delivery to the terrestrial planets and chemical inheritance from the protosolar nebula. Small body mechanical properties. Fragmentation and activity studies refine our understanding of small body tensile strength, porosity, and structure, critical for interpreting rubble pile models and for small body mission planning, landers, sample return. Heliophysics synergy. Timely detection of cometary responses to CMEs or solar wind streams helps quantify plasma-neutral coupling and can provide in situ-like probes of the solar wind at comet locations. Planetary defense and risk assessment. Understanding fragmentation and sudden mass loss is crucial for predicting the behavior of potentially hazardous small bodies and for designing mitigation strategies. Consequences of the missed high-rise window. Scientific losses. Loss of inner coma morphology at a critical time reduces ability to detect small, newly formed fragments and measure their separation vectors close to formation. Best chance to measure low relative velocities. Map jet origins on the nucleus and directly connect jets to surface features. Obtain high-precision short baseline astrometry that reduces uncertainties in non-gravitational modeling across perihelion. While many ground and space assets can mitigate some losses, the unique combination of resolution and vantage offered by HiRISE is not fully replaceable. How recovered observations can still address major science goals. Immediate multi-wavelength follow-up can detect delayed peaks, thermal lag or fragmentation, measure composition, and capture fragment evolution at later stages. Solar/heliospheric datasets can identify external drivers during the gap. Combined modeling and observed post-gap signatures can attribute causes to effects even when direct imaging is missing. Longitudinal studies, pre versus post-conjunction, still allow estimates of total mass loss, composition, and evolution, albeit with increased uncertainty on timing and impulsive events. Prioritized science objectives if reappearance is detected. 1. Establish activity state and search for fragments immediately, high priority. 2. Secure spectroscopy, optical/NIR and MM/SUB, to measure volatile production and compositional changes. 3. Intensive astrometry for orbit and non-gravitational force constraints. 4. High-resolution imaging requests, spacecraft/HST, if fragmentation or unusual morphology is present. 5. Polarimetry and dust size diagnostics to detect fresh ejecta and constrain grain properties. Below are concrete, prioritized observational actions to take during the current conjunction/gap, what can still be done now, and the actions to take immediately after re-emergence. Each item gives the goal, why it's high priority, suggested instruments/modes, cadence, and triggers for escalation. Observational priorities now, during conjunction/when direct imaging from Earth may be impossible. 1. Monitor the heliospheric environment, highest priority. Goal: detect CMEs, high-speed streams, solar wind conditions that could have impacted the comet during the gap. Why? Many comet responses, tail disconnections, enhanced sputtering, impulsive activity, are driven by solar wind/CME interactions. Knowing the timing of any heliospheric disturbance allows attribution even without direct imaging. Suggested resources: Soho-Lasco/C2/C3 coronagraphs, Stereo HI/Secchi imagery, SCAVR ACE solar wind monitors, Parker solar probe, if data relevant. Use coronagraph movie sequences and CME catalogs. Cadence: continuous/real-time monitoring, extract CME onset times and wind parameter time series for the comet's position. 2. Spacecraft coronagraph/inner heliosphere imagers, if geometry allows. Goal: detect the comet itself in white light coronagraphs/heliospheric imagers if it traverses their fields, especially stereo HI. Why? Even low-resolution detections constrain timing of major brightening or fragmentation events. Cadence: check archive near real-time images covering the conjunction interval, request higher rate products if available. 4. Maintain precise ephemeris and planning preparations. Goal: update orbit predictions accounting for non-gravitational uncertainty, prepare acquisition sequences for reappearance. Why? Small ephemeris errors compound over the gap. Having pre-computed pointing mosaics will save critical time on recovery nights. Actions: produce mosaics for likely reappearance windows, produce finder charts in multiple filters, compute expected brightness scenarios for planning exposure times. 5. Solicit and organize rapid response observing networks. Goal: coordinate ground networks spanning longitudes to maximize reappearance chances. Why? Reappearance may occur at low elongations. A distributed network increases chance someone sees it quickly. Actions: alert amateur/professional networks, CBAT, MPC, Comet telegrams, AVSO, prepare standard reporting formats for quick astrometry/photometry. Observational priorities immediately after reemergence, first detection to first 1 to 2 weeks. These are the critical measurements to obtain as soon as the comet is visible again. Prioritize in this order. 1. Rapid discovery confirmation and astrometry, within hours of first detection. Goal: get multiple astrometric positions to secure the orbit and reduce ephemeris uncertainty. Why? Precise orbit allows rapid pointing for follow UPS and constraining non-gravitational forces introduced during the gap. Instrument/mode: any telescope with good plate scale and time, even small telescopes are valuable immediately, deliver positions to the MPC promptly. Cadence: multiple observations across the first night and nightly for the first week. 2. High-resolution imaging, first possible night, highest priority if nucleus/fragments suspected. Goal: detect and resolve any new fragments, coma asymmetries, jets, or morphological signs of disruption. Below are concrete, prioritized observational actions to take during the current conjunction/gap, what can still be done now, and the actions to take immediately after reemergence. Each item gives the goal, why it's high priority, suggested instruments/modes, cadence, and triggers for escalation. Observational priorities now, during conjunction/when direct imaging from Earth may be impossible. 1. Monitor the heliospheric environment, highest priority. Goal: detect CMEs, high-speed streams, solar wind conditions that could have impacted the comet during the gap. Why? Many comet responses, tail disconnections, enhanced sputtering, impulsive activity, are driven by solar wind/CME interactions. Knowing the timing of any heliospheric disturbance allows attribution even without direct imaging. Suggested resources: Soho-Lasco/C2/C3 coronagraphs, Stereo HI/Secchi imagery, Scavre ACE solar wind monitors, Parker solar probe, if data relevant. Use coronagraph movie sequences and CME catalogs. Cadence: continuous/real-time monitoring, extract CME onset times and wind parameter time series for the comet's position. 2. Spacecraft coronagraph/inner heliosphere imagers, if geometry allows. Goal: detect the comet itself in white light coronagraphs/heliospheric imagers if it traverses their fields, especially stereo HI. Why? Even low-resolution detections constrain timing of major brightening or fragmentation events. Cadence: check archive near real-time images covering the conjunction interval, request higher rate products if available. Why? Inner coma structure and newly formed fragments are best detected at earliest epoch, small separation, highest S/n. Instruments: HST, if possible via 2, adaptive optics on large ground telescopes, VLT/sphere, Keck/NIRC2, Gemini with AO, or HiRISE if spacecraft opportunities exist. Filters/modes, broadband R or I for morphology, short exposures to avoid coma saturation, consider coronagraphic setups if nucleus very bright. Cadence: as soon as detection confirmed, then daily for at least the first week if activity or fragments are present. 3. broadband and narrowband photometry, first night and nightly. Goal: measure total brightness, AF, and track rapid brightness evolution. Why? Light curve reveals impulsive outbursts, steady sublimation, and roughly constrains dust production. Filters: standard broadband V/R/I, narrowband Comet filters, HB filters, if available for gas/continuum separation, CN, C2, C3, BC, RC. Cadence: nightly, with higher cadence, multiple times per night. If rapid changes occur, combine large and small telescopes to avoid saturation and maintain continuity. 4. Medium-resolution optical and NIR spectroscopy, first possible night and repeat. Goal: measure gas species, CN, C2, C3, NH2O, and continuum slope, detect H2O, CO2 proxies, near IR, where possible. Why? Composition before versus after conjunction reveals whether different volatiles dominated activity during the gap or if compositional changes occurred due to surface stripping/fragmentation. Instruments: VLT/X shooter, Keck/DIMOS or LRAS, optical, Gemini/NIRS, IRTF/SPX, NIR, JWST or NEOWISE if scheduling allows, space IR ideal. Spectral resolution: R1000, 5000 sufficient to measure bands and line fluxes, higher resolution for velocity structure if S/N allows. Cadence: initial spectrum at discovery, repeat within days and weekly thereafter during evolution. 5. Sub-MM observations of volatiles, within days to week. Goal: measure CO, HCN, CH3OH lines to quantify volatile production and search for supervolatile-driven activity. Why? CO/CO2-driven activity near perihelion or during thermal events leaves distinct signatures. Mass loss budgets require these numbers. Instruments: ALMA, IRAM 30M, APEX, SMA. Cadence: first observation as soon as the comet is in a usable sky position, repeat weekly or triggered by activity. 6. Polarimetry, early post-reappearance window. Goal: measure dust polarization as a function of phase angle and wavelength. Why? Polarization is sensitive to grain size, structure, compact versus fluffy, and freshness of dust, important to detect fresh ejecta from fragmentation. Instruments: VLT/FIRS-2 polarimetry, not/LFOSC polarimetry, other polarimeters on medium/large telescopes. Cadence: early single epoch then repeat as the phase angle changes and after any suspected outbursts. 7. Intensive astrometry orbit modeling, continuous during first month. Goal: constrain non-gravitational parameters, A1, A2, A3, introduced during the gap and refine future trajectory predictions. Why? Determines whether there was a significant momentum impulse, rapid outgassing, fragmentation, and improves ability to request future observations. Cadence: multiple astrometric points nightly if possible for first 1 to 2 weeks, then regular tracking. 8. High cadence follow-up if fragments or rapid brightening detected, hours, days. Trigger: resolved fragments, multiple nuclei, sudden magnitude jumps, greater than 0.5 mag/short interval, or unusual coma morphologies. Actions upon trigger: increase imaging cadence to hourly when feasible, for the first 24 to 72 hours. Frequent astrometry of fragments to measure separation vectors and velocities, multiple times per night. Black small square rapid spectroscopy of fragments and surrounding coma to check for compositional differences. Black small square request urgent HST or AO imaging if not yet obtained. Observational priorities in the medium term, weeks to months after reemergence. 1. continued multi-wavelength monitoring of gas and dust production. Track integrated Q, H2O, Q, CO, Q, CO2 proxy, AF, and dust-to-gas ratio with a cadence optimized to the comet's evolution, weekly by weekly. 2. Morphology evolution and dust dynamics. Map dust tail structures, synchrones/syndynes modeling to recover grain size distributions and ejection velocities. 3. Thermal and photometric phase function studies. Measure nucleus/near-nucleus brightness when coma contribution is minimal, late epochs, to estimate nucleus size and albedo. 4. Long baseline polarization and spectroscopic campaigns. Look for post-outburst changes in dust properties or the appearance/disappearance of volatile bands. Observational modes and technical guidance, practical details. Astrometry, aim for S/N greater than 10 per centroiding exposure, use non-saturated frames, provide UTC timestamps and calibration frames. Photometry, measure AF, use small aperture radii and correct for seeing, report aperture sizes and solar phase corrections. Narrowband, when possible use HB filter set, CN 388 nanometers, C2 514 nanometers, C3 405 nanometers, BC/RC continuum, otherwise approximate with broadband color indices and continuum subtraction. Spectroscopy, aim for absolute flux calibration, standard stars, to convert line fluxes to production rates using Hazer or vectorial models, report slit width and position angle. mm/sub, velocity resolution 0.1, 0.5 km/s useful for outflow velocity, absolute calibration critical for production rate estimates. Polarimetry, report phase angle and wavelength, use small apertures or radial profiles to separate nucleus versus coma polarization. Data products to prioritize for rapid sharing. Astrometry, MPC format, within hours of observation. Quick look calibrated images and photometry, magnitude, aperture radius, AF, posted to communal channels. Spectral line fluxes and production rate estimates with uncertainty estimates. Fragment positions and relative astrometry, nucleus versus fragment, for orbit/dynamics modeling. Decision rules/triggers that change priorities. Fragment detection or multiple nuclei, immediate highest priority imaging, astrometry, and spectral characterization. Rapid brightening, 0.5, 1 mag within 24H move to sub-hour cadence imaging and immediate spectroscopy, alert 2 facilities. Strong change in non-gravitational acceleration from initial orbit solutions, increase astrometric frequency and dynamical modeling. CME or solar wind event coincident with reappearance, prioritize coordinated plasma and remote sensing follow-up, and look for tail disconnections. Coordination, communications, and logistics. Rapid reporting, submit astrometry to the MPC and post quick notices on CBET/MPC/Comet discussion lists and social/professional networks to enable community follow-up. Centralize data, use a shared repository, institutional or community, for quick look products and reduce duplicative effort. Observation handoffs, plan longitudinal handoffs between observatories to maintain continuous coverage during the first critical days. If you want, I can produce a one-page to-request template for HST/KEC/VLT/ALMA highlighting the immediate priorities and exact exposure/filter recommendations tailored to estimated brightness. Generate an example nightly observing sequence, exposure times, filters, cadences, for a given telescope aperture and expected magnitude, provide the expected post-conjunction magnitude or the telescope you have access to and I'll tailor it.